All right, now it's time to do some examples involving these trig derivatives. So we are going to look at the first three problems on here in this video. And for each one of these functions, we are going to find dy dx. So we're going to start out with our first one. And you might want to get yourself a separate sheet of paper. That way you have some room. I've given myself some more space here. All right, so our first function is y equals negative 5x squared plus 3 tangent x. And this involves a type of derivative that we've seen before, a nice power rule there with a constant multiple. And then it's also going to incorporate one of our new trig derivatives. So sometimes it's just as much as that. A trig function also makes its way into another type of function that you've already seen in the past. So yeah, here we're going to be looking for dy dx, derivative with respect to x. And as I mentioned, we are going to use that constant multiple property here. Negative 5 times the derivative of x squared. And then you can also use that same constant multiple property if a constant is multiplying one of your trig functions. Nothing new there. So this is 3 times the derivative with respect to x of tangent x. Okay, and so now we get to tackle each one of those parts. So we have negative 5 and the derivative of x squared, remember, using the power rule, that's going to be 2x. And then plus 3 times our new thing, the derivative of tangent, which we derived in a previous video. We were using the quotient rule to help us figure that out, but you don't need to rederive that here. You should memorize the derivatives of the 6 trig functions. That way you can just pull out the fact that this derivative is secant squared x. Okay, so for our answer here, we get that dy dx is going to be negative 10x plus 3 secant squared x. And that's all there is to this first one. Okay, now for the second function, we have y equals the square root of x cosecant x minus 2. All right, this part you probably know how to handle that from a previous section. And then here in our first term, we have the square root of x times cosecant x. That's the multiplication or the product of two different functions of x here. So we are going to need to use our product rule. Okay, that is very important here. All right, so to use our product rule, we know we will have to end up taking the derivative of each one of those functions. So for starters, it might be a good idea to rewrite our function here with a rational exponent instead of that square root as it's currently written. Okay, so I'm going to do that here. Let's make that x to the 1/2 times cosecant x, and then minus 2. I think that'll make things a little nicer for us. All right, so then our derivative dy dx, we're going to use our product rule on that first term. We'll have our first function, first x to the 1/2, first times the derivative of the second. Okay, so x to the 1/2 times d dx of cosecant x. And then plus our second function times the derivative of the first. Okay, so that is our product. That's the derivative for this portion. And then for our constant there, the derivative is 0. So we could put a little minus 0 on the end there just to show ourselves that we handled that. All right. but it's not really going to have much of an impact. Okay, so we have x to the 1/2, and then the derivative of cosecant x is negative cosecant x cotangent x. Start making your flashcards or your Quizlet or whatever you're going to use. Memorize that guy. Okay, and then cosecant x, and then we've just got power rule on this other derivative here, 1/2 x to the negative 1/2. And the minus 0, we don't need to write that. Okay, so we could just leave it in this form, negative x to the 1/2 cosecant x cotangent x plus 1/2 x to the negative 1/2 cosecant x. That would be a-okay for these purposes. Since we're not doing anything else with the derivative, that's fine. Now, in certain circumstances, you might go on to use this derivative for something else, and then certain simplifications might be useful. So I'm not sure where entirely this might crop up, this particular function and its derivative, but a common simplification you might see would be to take out some of the common factors, which here would be a cosecant x for sure. And then also to factor out the lowest power of x. That's a pretty common thing. So we're going to factor out an x to the negative 1/2 here, just so you can see what that would look like. Okay, so we'll take out our cosecant x and then an x to the negative 1/2. All right, so in our first term, obviously we've still got that negative left over and a cotangent x. So negative cotangent x. And then to think about what's left when we factor x to the negative 1/2, factoring that out of x to the positive 1/2. Okay. If you need a little refresh on that, you can think about taking your original term, x to the 1/2, and dividing by whatever you've just factored out, x to the negative 1/2. And what we get there is x to the 1/2 minus negative 1/2, because when we're dividing like that, we would subtract the exponents. And that just turns out to be x to the first, or plain old x. So that's what we would get here. Okay, so I'm going to pop that in front of our cotangent x. X cotangent x. Okay, and then in the second term here, all that's left is the 1/2. Everything else would have gotten factored out. So you could leave it in this format as well. Okay. Or more likely, you'd probably put that x to the negative 1/2 out in front like this. X to the negative 1/2 cosecant x, and then 1/2 minus x cotangent x. Okay, so that's also a nice form for this solution. Now for our third example, we have y equals cosine x over 1 plus sine x. And this, as we can tell right off the bat, this is a quotient. Okay. And so we're going to use our quotient rule. So we're going to have dy dx equals low 1 plus sine x d high derivative of cosine x minus high cosine x d low derivative of 1 plus sine x all over low squared. So 1 plus sine x getting squared. Okay, So that's just writing down the form for the quotient rule. And now let's actually take the derivatives involved there. So we've got 1 plus sine x. Derivative of cosine is negative sine x. And then we have cosine, and over here, the derivative of 1 plus sine x. Well, the derivative of 1 is just 0, so that'll go away on us. And then the derivative of sine is cosine. Okay, so we have cosine x there. And then down in the denominator, I'm going to keep that factored as 1 plus sine x squared for now. Most of the time we're looking for ways to simplify these expressions, so keeping that factored is probably going to be nice for us. All right. Now, let's see here. Let's do a little distribution up top. We'll have negative sine x minus sine squared x and minus cosine squared x all over 1 plus sine x squared. Okay, we are on the lookout for simplifications, so how about let's factor out a -1 in the numerator. We'll have -1 times sine x plus sine squared x plus cosine squared x, and that is pretty nice. You might see a little trig identity popping up there. Notice right here we have our classic Pythagorean identity. Sine squared x plus cosine squared x equals 1. So we have -1 times sine x plus 1 all over 1 plus sine x squared. And now you might see another little something we could simplify there. Up in the numerator, in those parentheses, we could write those terms in the opposite order. And it's just the same as our factors on the denominator. We can cancel out a 1 plus sine x, taking us down to just one of those in the denominator. So ultimately, for our derivative, we end up with -1 over 1 plus sine x. And there's our answer. Now in the next video, we'll tackle the rest of our examples.